All right, it looks like we're recording. Slides are shared. I think we're ready to go. Welcome to day 17 of C and Software Tools class. Today we're going to be talking about a part of the C compiler that we've really only used a tiny bit. We've used the preprocessor, and we've used it for a couple of things, but it can do more than what we've been getting out of it. We'll see some of that today. And it'll help explain some of what we've been using since the start of the semester. I don't know if I said, the part we'll be covering the preprocessor, that first stage of compilation. And one thing that's neat about it is a lot of other languages you're accustomed to using don't really have a stage of compilation like this. Java doesn't have a pre-processing stage before it lets the compiler see your code. It's kind of ugly, but in being ugly, it can do some things that that would be harder to do if we just had to write them in the regular C programming language. Any questions before we can try and get started? So here's some of what we're going to try to cover today. We'll talk about things you can do with the preprocessor, some things that we've been doing since the start, and some new tricks that we're going to see for the first time today. You know what the preprocessor is, at least you know a little bit about it. It is a dumb-ish text-based stage of compilation that just does text manipulation of your source code before the regular compiler even sees it. I say it's dumb-ish because it doesn't have to understand all of the syntax of C. It doesn't understand all the syntax of C. It just does basic text-based substitution, like going and getting the contents of a header file so the compiler can see that before it sees the rest of your code. Defining constants, which are basically just text replacement rules in your source code. We'll see you can also use it to do some fancier substitution rules in your program, things that are normally called macros. And we'll see support for conditional compilation, ways to include or leave out whole blocks of code based on tests that are done while your code is being compiled. Now, I mentioned you already know a couple of things you can do with the preprocessor. We've mostly been using it for includes and for defining named constants. We're really just using a tiny part of the preprocessor's macro expansion mechanism, and we'll see more of that today. When we use the preprocessor to define a named constant, we use a directive like the one I've got in the middle of this slide. Here we're saying essentially a substitution rule. When you see the token size, replace it with its definition. So whenever you see size, replace it with 256. We've called this a preprocessor constant, but officially it's an example of a preprocessor macro. And like I suggested, macros are things that get replaced during preprocessing. So when the preprocessor, once you've said this, when the preprocessor sees the word size, it replaces it with 256. And well, because that's what you said to do. And this process is called macro expansion, replacing macro names with their definitions. It's called expansion because, well, often the definition is bigger, so your source code gets bigger as you do this. The preprocessor is dumb, but it's not as dumb as it could be. When it's doing macro expansion, when it's doing this text-based substitution, it's expecting a whole token over on the left, so size here. It's not just looking for the string size and replacing it arbitrarily. It knows what tokens are, at least in the language. So if we say replace size with, well, here, 1024, we can make it easy for the preprocessor by putting spaces around size so it's clear that that's the token size. But even if we cram it up next to other syntax, like in my second example, the preprocessor can handle that. It doesn't need to see the token surrounded by spaces. It still can find that token and replace it. And it's also not fooled by the word size that shows up as part of another token. Like down at the bottom, I've got a variable, or I've got max size. It won't replace the word size there because it's only looking for the token size by itself as a single token, not part of a bigger token. And when I say token, I mean essentially the identifier, the same rules for finding identifiers that you would normally use in the language. So a sequence of character of numbers, letters, and underscores that starts with a letter or an underscore. So it's looking for a whole token like that. It won't replace a macro name if it shows up as part of a bigger token. You've learned that when you define a macro, well, you've probably learned you probably don't want to put a semicolon at the end of it because, like I'm showing at the bottom of this slide, that semicolon becomes part of the macro definition. So if you define size like I did there, 256 semicolon, the problem with that is the semicolon will be part of the expanded macro. So if you used size as part of an array definition like this, when size got replaced by the macro definition, the semicolon would also be part of the replacement, and then your code wouldn't compile anymore. So the takeaway from this is when you define a macro, it doesn't have to be just one number or one word. It really can include a whole line of text. For a macro definition like the one at the top of my slide, everything after the word fail is the macro definition. That's what fail gets replaced by. So you could put arbitrary C code in there if you wanted. Here, you could use fail kind of like it was a function. You just wouldn't have to put parentheses after it. And then based on how I defined this, it would automatically get replaced by a call to the exit function. This can be handy. Macros don't have to just be replaced by single terms. They could be replaced by any syntax you want. So you could use the preprocessor to kind of inject additional syntax into your code without having to type it all in yourself, without having to modify your code. We've seen that if you have a bad macro definition, and here I'm kind of pretending having a stray semicolon at the end is usually not what you wanted. This can be hard to debug because the semicolon that shows up in your code only gets put in by the preprocessor. So if you accidentally had a stray semicolon there and you compiled it, the compiler is going to complain about that semicolon. But if you go look at the line of code that it complains about, you're probably not going to see that extra semicolon because it got put there by the preprocessor. So bugs introduced by the preprocessor or by badly defined macros can be tedious to diagnose because they're a result of what the preprocessor does. For this reason, it's kind of handy to have the -E compiler option. We already talked about this maybe the second day of class. -big E stands for expanded. If you put -E, then you're asking the compiler to just run the preprocessor on your code and show the result of that. That's why I mentioned the word expansion before, because that's where the E comes from. I just want to see my code after the preprocessor has expanded all preprocessor directives. So if you run the compiler like this, it'll just run the preprocessing stage, and it'll show you the results of preprocessing, really just by printing them out on the terminal. So typically, you'd get a lot of output if you compiled your program like this. You might want to send that output to a file to make it easier to look at it, but this would let you diagnose problems that get introduced by the preprocessor. They'd give you a better chance of finding little mistakes like this, because they give you a chance to see what happens after pre-processing. Questions before we move on? I saw there was something that popped up on the chat. All right, so I've introduced you to the idea that a macro can expand to more than just one symbol. You might want to write a macro that expands to a whole bunch of stuff. Normally, when you define a macro like this one here, it's everything on the rest of that line of source code. Well, what if you want to make a macro that's too long to fit on a single source code line, or that's inconvenient to format if you just wrote it all on one line? You can do that. You can break the definition across multiple lines. You just have to put a backslash at the end of each line to effectively say this macro is continued, or the definition of this macro is continued on the next line. You can think of that backslash as escaping the line termination, saying, well, I'm going to end this line here, but it doesn't really count. The definition of the macro is continued on the next line. We'll use this to define macros that, again, are too long or don't look, they're not easy to read if we did write them all on a single line. So this would let us define macros that extend across multiple lines. I guess another note is macros can include other macros. This doesn't really take a whole lot of extra work from the preprocessor, but it's worth noticing. Over on the left, I defined a couple of macros. I defined pi with a kind of poor approximation of pi, and then I defined a constant 2pi. And in the second definition, I just used the previous definition. Over on the right, I did the same thing. I just did it backward. I accidentally defined 2pi before I had even defined the pi macro. Both of these will expand to the same thing because of how the preprocessor works. So if your source code included 2pi, it's gonna say, oh, I've got a definition of 2pi. I just replace that by 2 times pi. So this will get replaced by its definition 2 times pi. And then even after expansion, the preprocessor will look at its result and say, oh, there's another macro that got introduced. I've got a definition for pi. And even though here you defined pi first and here you defined it second, it doesn't matter. When the compiler or the preprocessor sees that pi there, it's going to say, oh, I've got a definition for that. I'll replace it by 3.14. And either way, you end up with the same resulting code. So one takeaway from this is macro definitions can use other macro definitions. They can be built out of smaller, simpler macro definitions. And in general, the preprocessor keeps replacing macros by their definitions until there are no new macros to replace with their definitions. We'll use this a little bit. It means we can write code that uses other preprocessor definitions. Mostly what I've told you so far is when you define a macro, everything on the rest of that line is part of the macro definition. So it's what the macro gets replaced by. And if you need to stretch it across multiple lines, you can use a backslash to escape the line terminator and continue on to the next line. Those are the two new things that I've shown you. By themselves, they're not that useful, but this next thing can be awfully useful. Macros can take parameters. We haven't done this yet, but if you define a macro like I'm doing here, right after the macro name, you put an opening parentheses. Anything you put inside that parentheses is taken as the name of a parameter that macro can use. If you have multiple parameters, and I've got an example of this on the next slide, you can do a comma separated list. So you could have more than one parameter if you needed. And then in the definition, you can use whatever names you specified as parameters. What does a parameter do in a macro? I've got some examples that illustrate this. If I had to try to describe it, just like any other macro, when it sees you use ×2, it replaces it by its definition, by x times 2. But for x, it doesn't just use the character x, it uses whatever you pass in inside these parentheses. So it replaces the macro with its definition, but any occurrences of the parameter, it replaces with whatever syntax is passed in. What do I mean? Well, down here is an example of using this ×2 macro. And like its name suggests, it just takes whatever you pass in and multiplies it by 2. by replacing it with that thing times 2. So if you said expand times 2, but use I as x, you'll get the replacement x times 2, but instead of x, you get the I that you passed in. So the x becomes whatever the value of the parameter is, and the rest of the macro definition just gets copied verbatim. You could use this to stick arbitrary syntax in as the value of the parameter. So here I put a sub k as the parameter. The macro definition gets expanded to a sub k times 2, and the surrounding syntax gets left unchanged. So because I had a +1 over here, that +1 is still here after the macro is expanded. So this lets you compute really arbitrary expressions inside a macro. And when they get expanded, you get whatever you gave as the macro definition, with the parameters replaced by whatever you passed in. This is really a third type of parameter passing that you may not have seen until now, until you've seen it in the preprocessor. Some people refer to this as call by name. You've seen call by value, where functions get copies of the value of their parameter. You've seen call by reference, where functions can access the actual parameters because they get references to them. Well, here, this is referred to as call by name because when the macro is expanded, it has whatever syntax you put inside the parentheses. It just has a copy of whatever you stuck in over here when you called the parameter or when you called the macro. This is going to let us do some neat things that we couldn't do in other parts of the language. So we've seen, what do I think I've told you here? I've said macros can take parameters. Here's the syntax for doing that. I've tried to describe how that syntax works, and we've looked at a couple of examples. I'll make one point, it's here in the slides, but I probably didn't say it well enough. For this to work, there can't be any spaces between the end of the macro name and this opening parentheses. If you accidentally put a space there, the compiler is going to think that all of that is just part of the macro definition. If I don't have an example of this in the slides, but if I had a space right here, it would think the name of the macro is times 2. It doesn't take any parameters, and paren x, close paren, blah, blah, blah. That's just its definition. So to make the compiler, to make the preprocessor see this as a parameter, you've got to put the parentheses right after the macro name. Questions before we move on? All right, what could we do with this that's kind of useful? We could make a function, or we could make a macro in the preprocessor that worked kind of like a function. But we can make it work in cases that an ordinary function wouldn't be able to work. And that's what I did here. I defined, this is typical of what you might do with the preprocessor. I defined a macro that computes the maximum of 2 values. Notice it takes 2 parameters, and I just had to separate them by commas. Its definition uses the ternary operator, and it does what you normally do to compute the max of 2 values. It compares them. If x is bigger, it evaluates to x, otherwise it evaluates to y. When you use this macro, you can call it as if it was a function. So here, the way I'm calling it on I and j looks like how you'd call a function. But instead of defining a function that does max, before the compiler even sees your code, the preprocessor replaces this by this thing over here. So this call to max gets replaced by the use of the ternary operator. It tests to see which is bigger between I and j, and then evaluates to either I and j based on that test. The nice thing about this is, this definition of max doesn't care about the types of I and j. Up at the top, it works fine for integer types. But if I tried to use it on doubles or floats or long doubles, it would still work just fine because the preprocessor just replaces, so down here I'm using doubles. It replaces this call to max with this definition. And this definition works just fine if A and B are doubles. as long as the two parameters can be compared with greater than, and they each have a value that can be evaluated, then this macro should be able to compute the max. It's kind of like I've defined a polymorphic function. That'd be easy to do in Java, but in C, we can't write a regular function that works for arbitrary types. But a macro can do that as long as its definition works for whatever types whatever types you call it on. So here we've got a macro for the max function that works for any of the built-in primitive types. Some functions that we've already seen were secretly macros, or actually, let me take that back. There are functions like fgetC and fputC that are regular functions, and you know them. They're for reading individual characters or writing individual characters to a file. There are good friends of these functions with slightly shorter names, getC and putC, that do exactly the same thing, except they might be implemented as macros. If you look at the documentation for fgetC, you'll probably see its good friend getC that does the same thing. It gets a single character from whatever file you give it and returns it. But instead of calling a separate function, these two are typically implemented as macros, which means they could be a lot faster. Here, when you use these two functions, you have the overhead of actually calling a function. And we've already made the point that could be a significant amount of overhead, especially if you call it a lot. But down here, these two just expand to whatever code it takes to get the next character from the stream. And since streams do buffering, when you try to read one character, they might read 1,000 characters and just give you the next one and store the remaining 999. Well, if these just have to get a single character out of the buffer, they could expand to a fairly short macro to do that. So they could be a lot faster than having to call a function. When you look at the documentation for these, you'll see, well, these top two are implemented as functions. These next two, for performance reasons, are typically implemented as macros. So some parts of the standard library are implemented as macros rather than functions, doing the same tricks we're learning how to do here. There are a couple of things you need to be careful of when you're defining macros, and that's what I'm going to try to talk about next. The preprocessor is, like I said before, it's kind of a dumb text-based stage of modifying your source code before the compiler even sees it. When you have a macro, it just replaces it with its definition. And that means there might be cases where the precedence you were expecting might not really happen after, or may not be the same after the macro is expanded. That's what I'm showing here. Let's say you have this ×2 function like we did before, and you gave it a parameter of I+1. Well, it's going to take that and expand it to code like I've got here on the right. So this is the definition of the macro, but X got replaced by I+1. And this is what the compiler is going to see. Problem is, this is probably not what you wanted when you said, take I+1 and double it. Well, if you called a function, that's what this would do. But if this macro call expands to this, it's not going to double I+1. It's going to you can just look at the precedence here. It's going to take 1 times 2 and then add that to I. So the I part doesn't actually get doubled. You probably wanted something like what I've shown up at the top. You probably wanted to compute I+1 and then double that. If you want that, and typically you do, you have to force the precedence of the macro to be what you want, usually by including parentheses. When people define a macro like this, they probably would define it more like the one at the bottom. They'd put parentheses around any of the parameters where they show up in the macro definition, and that's just to force whatever that parameter is to get evaluated first, without interfering with precedence in the surrounding macro syntax. So if you define your macro like this, whatever's inside these parentheses will get evaluated first before the ×2. So even if you called it with I+1 as the parameter, that'll expand to this syntax on the right. I+1 will get computed first, and then that result will get doubled. So in a typical macro definition, every occurrence of a parameter is going to have a pair of parentheses sitting around it. The same problem can happen with surrounding syntax. So backing up here, this is kind of a problem with the syntax inside the macro. If X gets expanded to a non-trivial expression, the problem is times has higher precedence than the plus. So the times is going to do its job before the add. If we want I+1 to get computed first, we had to put parentheses around it to make sure that happened. The same kind of problem can happen between the macro syntax and the surrounding code, and that's what I'm showing off here. Let's say you changed your definition of ×2. You remembered what we talked about last time with the left shift operator as being a really cheap way of doing doubling for a value, doing a multiply by 2. So let's say you define your macro like this. Take X, shift it to the left by 1 bit, and at least for non-negative numbers, that would multiply them by 2. The problem here is, what if you use this with some other expression around it? This call to this macro is going to get expanded to this syntax. And we did put parentheses around the X, so we get parentheses around the I here. The problem is, you may remember left shift has really low precedence, even lower than the plus. So when this macro gets expanded like this, it's going to compute 1 + 1 first, and then do the shift by 2 bits, which is probably not what you wanted. You probably wanted whatever the parameter was to get shifted, and then +1 to get added, at least looking at what you wrote down over here. We can fix this. We just need more parentheses. Normally, a macro definition, in addition to having parentheses around every occurrence of every parameter, it'll have one more set of parentheses around the whole thing, at least for macros that you expect to use as part of an expression. Here, ×2 is like a function call that you might use inside an expression. And if you're going to use this as part of a bigger expression, we can add parentheses to protect what's in the macro from the surrounding syntax. With this extra set of parentheses, the same macro expands to this, and now it'll do the bit shifting before it adds the 1, which is probably what you wanted. So this means the max macro that we saw a couple of slides ago really would be defined more like this. If you wanted a macro that computed the max of any 2 parameters, you'd probably have parentheses around every occurrence of those parameters, and one more set of parentheses around the whole thing to protect it from surrounding syntax. For macros that you expect to use as part of an expression, that's what you'd normally do. You could write a macro that you expect to use as a statement, and that's what I did at the bottom, a macro that expands to 1 or more statements that get executed. There, you'd typically put curly brackets around the definition of the macro, so that if you call this print2 function, maybe it expands to 2 calls to printf, but so that you can use it in place of any statement you want, putting an extra set of curly brackets around that will keep these 2 isolated from surrounding syntax. Then, for instance, if this was the body of an if statement, these 2 statements, these 2 calls to printf, would be treated as if they're the body of the if statement. So these 2 tricks are how we normally make sure that even after a macro is expanded, the stuff you pass to it doesn't interfere with syntax inside the macro, and the stuff around the macro doesn't interfere with what's inside the macro. Questions before I try to move on? I've been kind of giving you warnings about here are how things can go wrong in using a macro. And we've learned a couple of tricks for fixing that. Probably the biggest thing to be concerned about with using a macro, really the reason why, if you're looking at documentation and it says this may be implemented as a macro, the reason for that is because it may affect the parameters you pass to the macro, or it may affect what you can do or what you choose to do with the macro. Here's a simple example, and maybe the worst example is on the next slide. Remember, when you expand a macro, before the compiler even sees your code, the preprocessor is just replacing the use of a macro with its definition. So for this max macro, if you call it like this, it's going to expand to this code at the bottom. So if you passed in square root of something as the first parameter and sine of something as the second parameter, then those two parameters are going to get replaced with that exact syntax, which means it's going to look like this after expansion, which is going to be a little more expensive than you might want, because it's going to call square root and sine just to do this comparison. And then based on whichever one's bigger, it's going to calculate that same call again over on this right-hand side. So either square root or sine is going to get done twice, because this just gets expanded to this syntax. And if square root is bigger, it's going to compute based on what we wrote here. If square root is bigger, it's going to evaluate square root again for this part of the ternary operator. Otherwise, it's going to evaluate sine twice. Here, that's a little bit bad. It's going to be a little bit of extra computation that could have been avoided, computing the same function twice. This can be a real problem when macro parameters have side effects. Same idea here, same macro, but now I'm calling it with two parameters that both have side effects. So x++ not only evaluates to the current value of x, but it adds one to x. Same thing with y. If you use this macro, it gets expanded to this, and well, when it's evaluating this condition, x and y are both going to get incremented. And then based on whichever one is bigger, one of them is going to get incremented a second time. If x is bigger, this x++ will get evaluated, so x will have 2 added to it. If y is bigger, y++ will get evaluated a second time over here. So the problem is, if macro parameters have side effects, those side effects can happen multiple times, and there's not a quick fix for this. Those other things we could fix by adding parentheses, but suppressing multiple executions of expressions with side effects, there's not a good way to fix that. That's going to have to be the job of the programmer. If you're using a macro, then you've got to be careful not to pass in any parameters that have side effects. The code we were just looking at, if you want to compare x and y, and you want to increment them, and you know that max is implemented as a macro, then you better do the increment as part of a separate statement. That's really why the documentation has warnings about things that are or may be implemented as a macro. That's why it says those two that we just looked at, getC and putC, could be implemented as macros. That's a warning that you don't want to pass in any parameter values that could change the parameters, because those changes might get applied more than once. So I've given you some warnings, things that you have to be careful of when using macros. We've seen a couple of things about macros that make them nice. And one of them was, since they just expand to whatever you put in as the definition, no matter what the parameter types are, you could write macros that work for arbitrary types of parameters. We saw that with the max function. I'm showing another example here, writing a swap function that can work for any parameter types you want. So let's say you wanted to swap 2 integers, or 2 doubles, or 2 characters. In C, you'd normally have to write 3 different functions to do that, one for each type. And you would have to pass the parameters in by reference, by address, for swap to be able to do that. But since the preprocessor just expands to code right inside wherever you call a macro, it can do some things that a regular function can't, like the swap function. Here, give me either 2 parameters, or you give me any 2 parameters, A and B. This function will swap them by copying this macro will swap them by expanding to a little block of code that copies whatever's in A, copies B over A, and then takes whatever used to be in A and copies that over B. So with help from a temp variable, this will swap any 2 variables you want. You do have to help it out a little bit. You have to tell it the type of the things that you're swapping, because it uses that to make this temporary variable. There is a way to avoid this. We could write a smarter version of this macro that didn't even need that. I hoped to add that to the slides before class, but I ran out of time to do that. So we don't have that example. But for this version of the macro, as long as you help it out by telling it the type, it expands to code that'll swap any 2 variables you want. So if you've got a couple of ints, x and y, this call to the macro will expand to this little block of code, which will swap them. If you wanted to swap 2 doubles, you just have to change the type that you tell it. So macros, since they kind of stupidly expand to whatever their definition is, they can work in cases where regular functions couldn't do the job. There is another hazard of this. Since macros expand to syntax, they might expand to a lot more syntax than you expected. And here's an example showing that. Same max definition we've been using, but now I'm calling it to compute the maximum of 3 things, A, B, and C. I guess the way I wrote it here, first I figure out which is bigger between between B and C, and then between that and A. Or you could use it to compare 4 things, just with recursive calls to the macro. But whenever you do this, you need to think a little bit about what the expansion is going to look like, because if you're not careful, this can expand to a lot more syntax than you expected. To show this off, I took this first example where we're just computing the max of 3 things. Well, based on this definition, if we take this call to the macro and we expand it, it expands to this. I've just replaced this call with the definition, replaced x by A, and replaced y by whatever I passed in as B. So that gives me this, but the preprocessor isn't done with it yet. It's going to say, oh, there you're using max, and I've got a definition of max, so it'll expand each of these to a copy of the definition. And when it does that, you're going to get syntax that looks like this. So this smallish bit of code expands to this much larger expression. I didn't do it, but if you try this example, it expands to even more code. So macro expansion, especially if you have nested macros that you're using, it can expand to a lot more source code than you might have expected, or than what you'd get if you were just calling an ordinary function. Even though this max macro can compute the max of any primitive types, and a function couldn't do that, you do have to be careful about how you use it. I've got a few more preprocessor tricks. Questions before we move on? All right. There are a lot of things, a lot of little details to how you can use the preprocessor, and I'm just showing a couple of them here. One is sometimes you need to use the preprocessor to create a string. And there's a syntax to help you do that. Since the preprocessor gets whatever text is passed in as its parameters, like up here for this macro, I get dir and fname, And the macro has access to whatever text you put here and whatever text you put here. What if you want to build a new string that consists of bits of that text? Now, the problem is if you just put dir in quotes, it'll treat it as a string and it won't expand to whatever the value of the dir parameter is. What if you want whatever string, whatever text the user passed in, but you want to use that as if it was a string? Putting a pound sign in front does that. So I probably explained that badly. What I mean is, what if you want to know the exact sequence of characters the user passed in here, or the caller passed in here? If you put a pound sign in front of the parameter name, that's what it gets replaced by. Like I'm showing down here, dir expands to whatever the user passed in as a quoted string. Why do you need this? I tried to say this before, but I probably did a bad job. Why do you need a special syntax for this? If you had just put double quotes around dir, it wouldn't replace it at all. It would just think, oh, that's a string. But the pound sign says, I want you to give me a string containing whatever they passed in. And then you can use that the way you would use any other string in the language. Down here, I'm using it to build a longer string. I got whatever the first parameter was, that's this part of a path name, whatever the second parameter was, and a slash in between them. And since this happens before compilation, the compiler will glue these three together into one big string. So the pound sign, you can use that to kind of do cut and paste on text that's passed in to the macro to create additional strings. Whatever you get with the pound sign in front is going to be a double quoted string. What if you want to do that same cut and paste, but you want something that's not a string? You want something that could, say, be used as an identifier. We've got one more bit of syntax for that, and it's the double pound. Double pound is for when you want to glue together multiple parameter names, but you don't want double quotes around them. You could use this to create new things like new identifiers, new variable names based on the parameters you get. Here, I wrote a cat function. It expects two parameters, and it just takes the value of those two parameters and glues them together into one long sequence of characters. So if you call it with B123, the double pound sign takes the first parameter, the second parameter, gets rid of any space between them, and it evaluates to just the value of those two parameters. And again, you could pretend I'm using that to invent a new variable name here that I might use for something else. Either side of this could be a parameter, or it could be a literal if you want. So you could glue together X with any other syntax you want. It wouldn't have to be the value of another parameter. Why do you need the double pound sign? Well, if you just took X and crammed it right next to Y, the problem is the preprocessor wouldn't see that as parameter X followed by parameter Y. It would just see it as a single identifier XY. The double pound sign lets you say, give me the value of X, in this case B, give me the value of Y, but shove them right next to each other without any spaces in between. And again, if we tried to do that by just putting X right next to Y, it would think we were using a different identifier name. On your next exercise, you get to use this to invent new variable names, and you can use that to write little bits of syntax in your program with help from the preprocessor. Because the preprocessor can be used to write code, you could use it, often it's used to write little bits of code to help with things like variable initialization or with debugging. And that's kind of what I'm showing here. Let's say you wanted to be able to enable, or you wanted to print out some debug messages. Well, normally if you were going to add printouts into your code, you might write in code to call printf, and you'd have to make a format string and get it to print whatever you wanted. with help from the preprocessor, we can make it a lot easier to add in debug messages like that. And that's what this macro does. I called it report I because it'll print out the value of any integer you want. It'll print out that integer value. That's what the %d does. And whenever you pass in as the parameter, I just evaluate that, and that's the value of d. But I also report the name of the variable, or really whatever expression you want to print. And that's what this %s is going to be. How do I know the name of the variable you're printing? Well, since the preprocessor expands this, it knows whatever syntax you pass in as x. And remember, we just saw $x evaluates to a quoted string for whatever you pass in. So in this first call, it'll evaluate to I in double quotes. Here it'll evaluate to total. So this will expand to a little debug message that not only prints the value of a variable, but says the name of that variable as it generates a report. So this could make it a little easier to add debugging code, and as we'll see in a moment, to remove it when you don't need it. Questions before I try to move on? There to that part about removing it when you don't need it. We need to see a couple more things before we can do that. Questions? All right. You already know some of this. It's just since we're talking about the preprocessor, we'll remind you of one more thing we've always been doing with the preprocessor. We've been including headers. And you know that there's two ways of including headers. You can put the name of the header in angle brackets or in double quotes. And you know the difference for this. Angle brackets are for system headers. That controls where it looks for them. Like if you use angle brackets on a Unix machine, it'll typically look in places like /user include for headers. If you use double quotes, it's looking in things like the current directory. The nice thing is you can control the search path for either type of header. If you use a dash, or if you're using double quotes, $I is a GCC option that lets you specify other directories that the compiler should search for. So if you're writing a big project and you got a bunch of places where you've put header files, you could use this to get the compiler to search all of those places for files that are part of your project. Most of this you already knew. I think the -I we hadn't really talked about yet. You know about what include does. It goes and gets the contents of a header and pastes in the contents of that header in place of the include. So an include is like saying, go get this file and show its contents to the compiler before it sees the rest of the source code. And normally in a header, we put things like we've been doing, prototypes for functions, extern variable declarations, preprocessor constants. On your current project, you've started putting type definitions like struct definitions. You should generally, if you're writing a component, the header for that component should have anything that might be used by other components. So if your component has functions, then you put prototypes for those functions in the header so other code will know about them. So you can think of a header as advertising the external interface to a component. It says what other things should be able to use. But when you compile a source file, it's worth it to keep in mind that every header included by that source file or included by any header it includes, all that stuff. So any headers you include, any headers included by those headers, any other headers included by those headers, that all has to be collected by the compiler and reparsed and recompiled every time your source file, every time your .c file gets compiled. So keeping your headers as small as you can make the compilation process faster, and it can make it easier to maintain a big project. If you can keep something out of a header, it means you don't have to compile a bunch of code. You don't have to recompile a bunch of code that was using that header just to change that thing. On day 19, we'll talk a little bit more about how to organize a project to try to insulate code from changes to a header. But since a source file depends on all the headers it includes, either directly or indirectly, there's some value in trying to keep headers as small as you can. All right, we've got one more thing that the preprocessor can do for us that we haven't really talked about yet. And that is the preprocessor supports directives for conditional compilation. I mentioned this at the start of the lecture. You can mark blocks of code to be left in or left out, and it's the preprocessor's job to pay attention to these marks. Again, this is called conditional compilation. You can say what parts to leave in and what parts to throw away. This could let you write code that is more portable by deciding what sections of code to use based on the system you're compiling it for. This could let you, like we talked about a moment ago, it could let you leave out debugging code when you're compiling for production, but leave it in when you're compiling for development. We could use this to turn on debugging messages only when we need to have them. These are all things that conditional compilation will let us do. Conditional compilation is going to look kind of like what I'm showing at the bottom of this slide. It's going to be directives that look like if-else statements. Directives, in fact, this is a preprocessor directive that we'll learn in a couple of slides. #if says whether or not to include the next sections of code up to the matching #end if. So the lines in between these two preprocessor directives may get left in or not based on what condition you put after this if. So here I'm showing two directives, if and endif, that mark the start or end of a block of conditionally compiled code. Here's the full list of conditional compilation directives. So there's an if, there's an endif that we already talked about a little bit. There are else versions of these. So you can have else or else if. This is an abbreviation for else if that lets you decide to leave in one block or another. And we'll see in a moment that asking about whether or not a particular preprocessor symbol is defined, that's such a common thing that there are directives that do that, that are made to do that. They're shortcut directives for saying that. We'll start out with just if, else, and endif, and then we'll introduce these two in just a moment. If lets you ask about the value of preprocessor symbols, so really the same symbols that are used for macros, and decide whether or not to leave in the next block of code based on the value of those symbols. What can you ask about a symbol? Well, that's somewhat I'm showing here. If you've got a preprocessor symbol, so something that you may or may not have defined with #define, then if you put defined in front of it and the symbol name inside parentheses, this will evaluate to true if that symbol has a definition. So this lets you leave in or leave out blocks of code based on whether or not this given symbol is defined. Like I said a moment ago, this is so common in the preprocessor that we've got a shortcut syntax for that. If you want to ask, is this symbol defined or not, you can do it this top way, or #ifdef does that all in one directive. So if you want the next block of code to get included only if whatever symbol you pick is defined, you can do it this way, or you can do it like I'm showing here at the top. You can also ask about the value of symbols, and when I say the value of a symbol, I mean what you may have #defined it to previously. So you can use == to test if it has a particular value. You can use less than or greater than to ask whether its value is bigger than or smaller than some constant or some other symbol. You can even combine these with the usual logical operators. Uh, this one at the bottom, the next block of code would get discarded unless symbol X had a value that was bigger than 25, and whatever symbol Y is had a value that was less than 30. Keep in mind, all of this is evaluated before your code is even compiled. You're not writing ifs that'll get checked during execution. You're, with help from the preprocessor, you're deciding what blocks of code to leave in and which ones to get thrown away. Like I said, you might do this to handle portability issues. Let's say there's a header that you want to include, but the right header might depend on your system. Maybe there's one header you need to include for a Linux machine. If you're compiling on Windows, maybe it's a different header. And maybe you've even got a fallback header for other machines. Well, you could write an include that includes that header without committing to what it is, just by putting the name of the header in a preprocessor symbol. So that's what I'm doing here. But before I actually include it, I've got a block of code that decides what the name of the header should be based on what system I'm on. Let's say if you're on a Linux system, this preprocessor symbol Linux would be defined. If so, I'll set header to be linux.h. If I'm on a Windows machine, maybe I'll define Win32, and I'll set that same symbol to be something different on a Windows machine, or my fallback if I'm on some other machine. So this is the code we were just talking about. The preprocessor will either leave in this block or this block or this block based on the value of other symbols. And then whichever of these gets left in will decide what header you include. How do you decide which system you're compiling for? Well, that could come from other headers or other code that you've written. Or you could give that through your makefile. You could give that on the GCC line using the syntax that I'm showing right here. If you, for GCC, if you put a dash capital D and then any symbol name you want, it'll define that symbol just as if you had said pound define in your code. But this lets you define it without even changing your source code. So if you knew you were compiling on a Windows machine, you could use this option on the compiler. That would define this preprocessor symbol. And then when the preprocessor looked at that symbol, it would decide to include this little block of code. If you were compiling on a different machine, you could give a different option to the compiler and activate different parts of your code. This, we already saw this option when we were talking about the assert macro. You may remember we had the -d in debug macro for turning off assertions. That was really the same option. It's just to turn off assertions, we had to define the in debug, no debugging symbol. And we did that with -d in debug. Well, this is showing that that same trick works for any symbol you want. If you define it like this, it'll show up as defined in the preprocessor. And if you looked at its value, it gets a value of 1 by default. A couple of slides from now, I can show you how to set that value. So this is what conditional compilation does. And this is an example that shows how you could use it to include some portability support in your code. One place where it often gets used is to solve a problem that we've avoided so far. We've picked projects where we could code around this. But in general, you might have to worry about the same header file getting included more than once. So far, we've been able to structure our headers so that didn't happen or didn't need to happen. But you can't always do that. Let's say you've got a file like main, and it includes a.h and b.h, maybe 2 other headers that you wrote. And a.h might use some other header, and maybe b.h also needs that header. Maybe these 2 need some types that are defined in c.h. So they both include it. Problem is, when you compile main, this header is going to get included twice. When you compile main, the preprocessor is going to go get a copy of a.h, and when it sees the include of c.h, it'll get a copy of c.h. And then later, further down in main, when the preprocessor goes and gets a copy of b.h, it'll get another copy of c.h. So the same code for c.h would show up twice when you're compiling main. Is that bad? Well, it's bad for some things. The compiler doesn't care if it sees the same, it depends on what's in c.h. The compiler doesn't care if it sees the same prototype twice. It doesn't care if it sees the same extern definition twice, as long as they agree. But it doesn't like to see the same type definition twice. If c.h defined a struct, then the compiler is going to see that same struct definition twice when it's compiling main, and that's going to make it unhappy because it's not going to realize that that's a copy of the same thing. It's going to think you're trying to compile the same struct twice, and it's going to complain about that. So we've got to keep this from happening. It seems like a silly thing to worry about, but this really could happen, and I tried to sell you on this idea a moment ago. If a.h needed something from C and b.h also did, and if main used both of those, a header could easily get included twice. We can fix this, and this is kind of ugly, but it's the standard way of fixing this, with help from conditional compilation. Most headers contain what's called an include guard. And it's there to keep anything bad from happening if the same header gets included twice. To fix this, whoever wrote c.h, it's their job to wrap everything in their header in conditional compilation. Most headers do this inside the header. That conditional compilation is designed to keep whatever's in c.h the first time it shows up. But any subsequent occurrences automatically get thrown away. Here's what an include guard looks like. So this is the typical way of defining it. I'll wrap, like I said, the whole contents of the header in conditional compilation code. So here's the start of the header. You can think of this as saying, only include the rest of the stuff if you have to, or throw away the rest of the stuff if you've already seen it. And this pound end if is just the end marker for that. So everything inside only gets included if this identifier is not defined. For this identifier, we normally just pick a name that matches the name of the header. So if this is a header file named c.h, we could just pick a symbol name c_h. We just made up that symbol name with the expectation that, well, it's not defined. We just made it up. It's probably a symbol that nobody's using. So it's not normally going to show up as defined. The rest of this header only gets left in if this symbol is not defined. So the first time we see this header, c.h hasn't been defined yet. So the compiler is going to see everything up to the end if. But inside the header, the first thing we do is define that symbol. The plan here is, if this header gets included again and it checks the same thing, and it will if it's the same code, this will show up as already defined. So the rest of the body of the header will be left out. I feel like I did a bad job explaining that. Let me try to say it again real fast. Let's pretend you've got a situation like this. The same header, through nobody's fault, gets included more than once. When the compiler sees the header the first time, this symbol name that I just made up won't be defined. So this if end if will say, oh, leave in all the code down to the matching end if. So this will all get left in. The compiler will see the contents of the header, but the symbol will get defined. If through some other path the same header gets included again, now c.h is defined. So the compiler will leave out the rest of this code, and it'll only get seen once. That's probably a long explanation for a simple idea, but this is intended to prevent the compiler from seeing the same header code twice. It's kind of a silly thing to have to fix. It's normally fixed via the preprocessor, so they never really developed a better way of doing that in the language. It's standard to just avoid duplicate includes with help from the preprocessor. Questions before I try to move on?
Where would that go?
So in any header, this would normally be at the very start of the header, and this would normally be at the very end of the header. And you'd pick a name that is specific to the header. Like if everybody used the same name for this, it wouldn't work. You have to pick a name that is kind of tied to the name of the header, that's unique to the name of the header. Hopefully I answered your question. You don't really have to do this with every header. Any header that might get included more than once will normally have an include guard. And since you can't really know if your header might get included more than once, you'd normally have this wrapped around the body of every header.
Dr. Sujal?
Yeah.
Is that like a C_H? Does that like as a kind of library, or it is?
It's just a name I picked that matches the name of the header.
So we can write any header there. Like, I mean, it doesn't have to have like a C_H.
It's normal to use a naming convention like this. So if you wouldn't use, like if your header was named database.h, you could use all caps database_h as the symbol that keeps up with whether or not your header has been included.
No, I mean, like, can we write like X_Y right here?
Well, this is just I worry that I don't understand your question. You can use any symbol name for this. If your header was named C.H, it's probably a bad idea to use X_Y as the symbol name that keeps up with whether or not it's already been included.
Okay.
I mean, you could do it and it would work as long as no one else was using that symbol name, but by convention, you would pick a name here that matches the name of your header, just to try and make sure no one else was using that name.
So, I got it right now.
Okay.
I missed the connection.
So we said, yeah, so again, you pick a name here that's kind of tied to your header name, because if everybody's doing this trick, we each need to try to use each header needs to try to use a symbol name that is associated with that header name. I said before, conditional compilation is also kind of handy for debugging, and there are a few things I can show you on this. For one, remember from maybe the first or second day of class, I think I pointed out that commenting out code is usually a bad way to exclude it from compilation, in particular because comments are not guaranteed to nest. If you take a block of code that you want to leave out, debugging code or not, and you put a start of a comment at the start and an end of a comment at the end, it's common for people to do that, but it could be a bad idea, because what if you comment out a block of code and then you comment out a block of code that contains that first block of code? That's not guaranteed to work. Comments are not guaranteed to nest like that, but conditional compilation code is guaranteed to nest properly. So instead of commenting out debugging code, you could just use conditional compilation. What if at the start of your debugging code, you have an if-def that says only include this if the debug flag is turned on? Then you can have a block of commenting code up to the matching end if, and then without even having to edit your code, you could decide whether or not to leave that in by defining the symbol or not. And even if you've got other blocks of conditionally compiled code inside it, this is still guaranteed to work, whereas commenting is not. And like I said, you could go back and turn this on or off without having to go edit all of your comments. That macro we looked at a moment ago would be awfully handy for this. Remember, we had this report macro that would print out any variable or really any expression you want along with its name. But what if you decided you wanted to turn off all of that debugging? If you had done this with a preprocessor macro, you could make it really easy to turn it all off at once by just picking your definition of that macro based on whether or not debugging is turned on. And that's what I've done here. Here's how you could use this macro. If debugging is turned on, all of these report I's get replaced by this call to printf. If debugging is not turned on, well, I still define report I just define it to expand to nothing. So if this debugging is turned off, all of these debugging messages go away, but I can easily turn them back on by changing the value of the symbol. So this makes it, this is what assert does internally, and it makes it easy to turn on or off all of your debugging code without having to go hunt it in your source code and comment it out or delete it. This way you can turn it off and then turn it back on later if you need to debug. One more thing I can show you, and it's really just finishing what we talked about before. Like I said, if you've got some symbols that you're using and you want it to be easy to define them or not, or to pick values for them, you've already seen the -D compiler option that lets you define any symbols you want. So if you say -D debug, that defines the debug symbol, and if you don't say otherwise, it gets a value of 1. So inside your make file, you could easily turn on or off all of your debugging code. To finish explaining this syntax, if you didn't want a symbol to have a value of 1, you could pick any value you want for it just by going on and saying equals and then any string you want it to have. So this is equivalent to saying #define name space bill in your source code. This lets you pick, it just lets you define it without having to change your source code. Since the shell processes this, if you need a space inside the value of a preprocessor symbol, if you don't do anything special, it'll think that's, if you put a space here, like I'm doing over here, hello world, if you don't do anything special, it'll think message just has the value hello, and it'll think world is the next option. But like I did here, if you wrap double quotes around that, including the dash, that says to the shell, this is all one command line argument, even though it's got some spaces in it. And this will let you embed spaces in the definition of any symbol value that you need. You just have to keep the shell from breaking up the arguments at those spaces. And that's all I got to say for the preprocessor. This, on your next exercise, you get to use this to write some kind of ugly code, but code where you use the preprocessor to help write little bits of C for you. That is sometimes handy, but some of the other stuff we saw, like defining macros or debugging behaviors from the preprocessor, those are more typical of what people would do in production code. I'll hang around if people have questions. Otherwise, we're done for today and we've used up most of our time. Let me go ahead and stop the recording.